Real images of what NASA discovered on Jupiter's oceanic moon, Ganymede. What do we expect to see if we point our telescope towards Ganymede? Is it bright or not? Ganymede has an albedo of about 43%, meaning that it can reflect back to us the 43% of the total solar radiation hitting on its surface. Also, as they were suspecting from density measurements when astronomers studied Ganymede by means of the near-infrared spectroscopy, they found strong water ice absorption bands, thus confirming the presence of water ice on Ganymede. However, the leading hemisphere is brighter than the trailing one, and this is probably due to the presence of extended ice caps in the leading hemisphere, while the trailing one seems to be enriched in sulfur dioxide. Talking about its internal structure, here's how Ganymede appears to be. Differentiated layers appear to contribute to its composition. In particular, we have an internal structure consisting of iron sulfide and iron core, a silicate mantle and outer layers probably made of water ice and liquid water. In the 70s, NASA scientists began to suspect that Ganymede had a thick ocean between two layers of ice. After 20 years, they sent a mission to confirm or reject this hypothesis. The mission's name was Galileo. Later in this video, we will see what Galileo found. One thing left to discuss is whether Ganymede has an atmosphere or not. When we launched HST, we found that Ganymede does have one. It is actually a tenuous atmosphere made of oxygen. We know this because HST observed air glow of atomic oxygen in the ultraviolet wavelengths. Such air glows are excited when molecular oxygen is disassociated by electron impacts. Spectroscopy is a really powerful instrument we have to investigate other worlds, and it is based on the light emission of absorption of electronic transitions of elements. So if spectroscopic studies suggest the presence of oxygen lines, then there is no doubt oxygen is present on Ganymede. Also, the existence of such an oxygen atmosphere implies that an ionosphere should exist. We expect that high-energy electrons coming from both solar radiation and magnetosphere of the moon ionize oxygen, contributing to building an ionosphere. Okay, ladies and gentlemen, now we know a lot about Ganymede. We introduced it to you, but until now you've barely seen it. That's why we're going to show you the most beautiful pictures of Ganymede we have taken so far. All of the pictures we are about to discuss were taken from probes, flybys all over the years. We never had a dedicated mission to Ganymede, meaning that no spacecraft has yet orbited Ganymede, but there have been multiple proposals to do so, including the JUICE mission, which is currently under construction. This is one of the pictures taken from the Pioneer 10 mission, which performed a flyby in 1973 as it passed through the Jupiter system at high speed. Pioneer was the first spacecraft to obtain close-up images of Jupiter, Callisto, Europa, and Ganymede. The mission was useful to determine the moon's physical characteristics we discussed so far. Thank you, Pioneer. 6 years later, the famous Voyager 1 and 2 probes passed through the Jupiter system, as they were designed to study the outer solar system and interstellar space beyond the Sun's heliosphere. Data from those flybys were used to redefine the size of the moon. This Voyager 2 color photo of Ganymede, the largest Galilean satellite, was taken on July 7, 1979 from a range of 1.2 million kilometers. Most of this portion of Ganymede will be imaged at high resolution during the closest approach with the satellite on the evening of July 8, 1979. The photo shows a large, dark circular feature about 3,200 kilometers in diameter with narrow, closely spaced light bands traversing its surface. The bright spots dotting the surface are relatively recent impact craters, while lighter circular areas may be older impact areas. The light branching bands are ridged and grooved terrain first seen on Voyager 1 and are younger than the more heavily cratered dark regions. The nature of the bright region covering the northern part of the dark circular feature is uncertain, but it may be some type of condensate. Most of the features seen on the surface of Ganymede are probably both internal and external responses of the very thick, icy layer which comprises the crust of this satellite. Here instead, you can see a cool picture as acquired by Voyager 1 during its approach to Ganymede. The image shows detail on the surface in a northern hemisphere region. It shows a variety of impact structures. The most striking features are the bright ray craters, which have a bluer color, appearing white against the redder background. Ganymede's surface is known to contain large amounts of surface ice, and it appears that these relatively young craters have spread bright, fresh ice materials over the surface. However, the record for the closest flyby is owned by the Galileo spacecraft. It passed just 264 kilometers from the surface of Ganymede. It actually did 6 close flybys of Ganymede. Here's a simulated flyover of an area on Ganymede, based on images taken by NASA's Galileo spacecraft. It takes the viewer over rugged, ancient terrain that is interrupted by a bright, icy swath of more recent surfacing. Parts of the dark terrain are heavily cratered, testifying to their ancient age, but other parts have been deformed into deep grooves by stretching and faulting. Other missions that visited Ganymede were New Horizons and Juno. Both of them performed distant flybys at a range of 100,000 kilometers. However, in June of 2021, Juno performed a closer flyby of about 1,000 kilometers. On that occasion, additional images of the surface were collected. Here are some. Take a moment just to look at them and appreciate the beauty of our universe. Finally, I want to show you an image that is worth 1,000 words. On the left side, you have a picture of Ganymede taken by HST in 1996, and on the right side, you can see the giant steps technology made between 1996 and 2021. In fact, the right panel picture was taken by Juno in 2021 and shows features of Ganymede as seen in the infrared domain. What a time to be alive. Real images of what NASA found on freckled moon Europa. Jupiter's moon Europa is beautiful. Have you ever seen it? Here it is. This is not an artist concept. This isn't an illustration. This amazing picture is showing the fascinating surface of Jupiter's icy moon as seen by the Galileo orbiter in the 1990s. This is the color view of Europa that shows the largest portion of the moon's surface at the highest resolution. Color variations across the surface are associated with differences in geologic feature type and location. For example, colors help us to distinguish areas containing water ice from the ones which include non-ice components. We will talk about it later on in this video. Take a look at this picture. It shows the 4 Galilean moons from left to right, starting from Io and ending with Callisto. New Horizons spacecraft had the honor to capture these pictures, and NASA put them together in a single family portrait of Jupiter's moons. As you can clearly see, Europa is the smallest of them. It is 3,120 kilometers in diameter, and New Horizons took this picture from a distance of about 3 million kilometers. If you look closely, you can notice that Europa's surface is different from the surface of other moons. It is an icy, smooth surface that likely conceals an ocean of liquid water. Why is it so smooth? It seems craters are almost absent on Europa's surface. While Europa is actually the smoothest known object in the solar system, it lacks large-scale features such as mountains and craters. Considering that Europa is constantly hit by cometary bombardment, we explain this smoothness by saying that the surface is really young, with an estimated age which is about 20 to 180 million years old. This finally means that the surface is constantly and rapidly changing. However, does this mean that Europa's surface is boring? It is a surface without any features to note. Well, that's not exactly so. Scientists think, for example, that Europa's equator may be covered with ice in an unusual way. Imagine polar regions on Earth. It has nothing to do with them. According to one study, instead, icy spikes called penitents are covering the moon equator. They could be up to 15 meters high and vertical. Unluckily, we don't have pictures of these unusual features, but radar and thermal data are consistent with this interpretation. Also, as you can see from this picture taken by the Galileo orbiter spacecraft, Europa has freckles. These reddish spots and shallow pits pepper the enigmatic ridge surface of Europa. Each of them is about 100 kilometers across. The dark spots are called lenticulae, the Latin term for freckles. Their similar sizes and spacing suggest that Europa's icy shell may be churning away like a lava lamp, with warmer ice moving upward from the bottom of the ice shell, while colder ice near the surface sinks downward. As we can read on the NASA website, surface features indicate that Europa could host life. Europa's surface has very few craters, indicating that recent or current geologic activity has removed the traces of older impacts. The paucity of craters, coupled with other evidence, has led scientists to surmise that there could be an ocean of liquid water beneath Europa's surface. Where there is water, there could be life. This is why Europa is a target of current interest for the study of the possibility of non-Earth life. A follow-up spacecraft to Galileo will be Europa Orbiter, which should determine whether or not Europa has an ocean. Europa orbits Jupiter in 3.5 days at a distance from it of about 670,900 kilometers. Its orbit eccentricity is very small, with a value of only 0.009, which means that the orbit itself is nearly circular. Europa is being pulled and stretched by Jupiter and other nearby moons. As it comes slightly nearer to Jupiter, the gaseous planet gravitational attraction increases, causing Europa to elongate toward and away from it. As Europa moves slightly away from Jupiter, Jupiter's gravitational force decreases, causing it to relax back into a more spherical shape. This creates tides in its ocean. This tidal flexing gives Europa a source of heat, possibly allowing its ocean to stay liquid. However, Europa's most striking surface features are a series of dark streaks crisscrossing the entire globe called linea. These linea suggest that Europa's surface could host volcanoes. This image, taken by the Galileo orbiter, shows features that may flow from ice volcanoes. It was taken by the Galileo system during its 7th orbit around Jupiter. The sun is illuminating the scene from the left. On the northwest corner of the image, one can see features with shapes similar to lava flows on Earth. The southern feature instead appears to have flowed over a ridge along its western edge. This beautiful picture clearly shows the presence of linea. Color variations across the surface are associated with differences in geologic feature type and location. For example, areas that appear blue or white contain relatively pure water ice, while reddish and brownish areas include non-ice components in higher concentrations. The polar regions visible at the left and right of this view are noticeably bluer than the more equatorial latitudes, which look more white. This color variation is thought to be due to differences in ice grain size in the two locations. Okay, now we know a lot about the surface. What about the internal structure? As we've already said, it is estimated that Europa has an outer layer of water around 100 kilometers thick. Underneath a crust of ice, there might be an ocean of liquid water. Also, in order to understand what lies in the deepest layers, astrophysicists studied Europa's magnetic field. Recent magnetic field data show that Europa has an induced magnetic field through interaction with Jupiter, which suggests the presence of a subsurface conductive layer, thus reinforcing the liquid water hypothesis. Europa is also likely to contain a metallic iron core. One interesting thing about Europa is that you could die if you were exposed to its radiation. The radiation level at the surface of Europa is equivalent to a dose of about 5,400 millisievert per day, an amount of radiation that would cause severe illness or death in human beings exposed for a single Earth day. The duration of a Europan day is approximately 3.5 times that of a day on Earth, resulting in 3.5 times bigger radiation exposure. Exploration of Europa began with the Jupiter flybys of Pioneer 10 and 11 in the 70s. The first close-up photos were of very poor resolution compared to later missions. Here's how Europa looked like to the eyes of the Pioneer 10 spacecraft. Then in 1979, it was the time for the two Voyager probes. They traveled through the Jovian system, providing more detailed images of Europa's icy surface. It was with the Voyager mission that scientists started to speculate about the possibility of a liquid ocean underneath. Here are some pictures taken by the Voyager probes. But this was not the end. In the 90s, NASA decided to understand better Jupiter and its moons, as well as the asteroids Gaspra and Ide. So they decided to launch a probe, the Galileo probe. Galileo arrived on Jupiter in 1995 after gravitational assist flybys of Venus and Earth, and became the first spacecraft to orbit Jupiter. Good job, Galileo. The vast majority of the images we showed you so far were in fact taken by the Galileo spacecraft, but I want to show you an incredible collage. The mosaic on the right of the south polar region of Jupiter's moon Europa shows the northern 290 kilometers of a strike-slip fault named Astropelenia Linea. The entire fault is about 810 kilometers long, the size of the California portion of the San Andreas Fault on Earth, which runs from the California-Mexico border north to the San Francisco Bay. The left mosaic shows the portion of the San Andreas Fault near California's San Francisco Bay that has been scaled to the same size and resolution as the Europa image. Each covers an area of approximately 170 by 193 kilometers. The red line marks the once active central crack of the Europan Fault right, and the line of the San Andreas Fault left. They look very similar, don't they? The only difference is the mechanisms that produce them. As for Europa, fault motion is induced by tidal forces and gravitational tug from Jupiter. Here on Earth, large strike-slip faults such as the San Andreas are set in motion not by tidal pull, but by plate tectonic forces from the planet's mantle. Real images of what NASA discovered on Callisto. It was only in 1979, with the advent of Voyager 1 and Voyager 2 flybys, that the real breakthrough happened. The two spacecraft, which goal was to exit the solar system, passed close to the moon and imaged more than half of the Callistoan surface with a resolution of 1 to 2 kilometers. They also measured mass, temperature, and shape. This picture of Callisto was taken by Voyager 1 Tuesday, March 6, 1979, during its approach to Jupiter's outer large satellite. The spacecraft was 350,000 kilometers from Callisto at the time and shows features about 7 kilometers across the surface. The prominent bullseye-type feature in this picture is believed to be a large impact basin, similar to Mare Oriental on our moon. The brighter circular spot is about 600 kilometers across, while the outer ring is about 2,600 kilometers across. This is the first recognized basin in the Jovian system and supports the concept of an old surface for Callisto. The darker color of Callisto, about half as reflective as Ganymede but still twice as bright as our moon, suggested that its upper surface was a dirty ice or water-rich rock frozen at Callisto's old surface. Therefore, with the temperature of about 120 degrees Kelvin or minus 243 degrees Fahrenheit at the equator. After Voyager encounters with Callisto, we had to wait until 1995 to have a second round of exploration. It was 1994 when the Galileo spacecraft flew by it 8 times, the last having taken place in 2001 at a distance of 138 kilometers to the surface. The Galileo orbiter gave us amazing pictures of Callisto. Voyager had a resolution of 1 to 2 kilometers, as we've already said, but Galileo delivered a number of pictures with a resolution as high as 15 meters of selected areas of the surface. The analysis of high-resolution near-infrared and UV spectra obtained by the Galileo spacecraft has revealed various non-ice materials, such as magnesium silicates and possibly ammonia and organic compounds. Here are, of course, some pictures taken from Galileo. This one, for example, shows bright scars on a darker surface that testify to a long history of impacts on Jupiter's moon. As we can read on NASA's website, the picture taken in May of 2001 is the only complete global color image of Callisto obtained by Galileo, which has been orbiting Jupiter since December of 1995. Callisto's surface is uniformly catered but is not uniform in color or brightness. Scientists believe the brighter areas are mainly ice and the darker areas are highly eroded ice-poor material. These 4 views of Jupiter's second largest moon, Callisto, highlight how increasing resolutions enable interpretation of the surface. In the global view, top left, the surface is seen to have many small bright spots, while the regional view, top right, reveals the spots to be the larger craters. The local view, bottom right, not only brings out smaller craters and detailed structure of the larger craters, but also shows a smooth, dark layer of material that appears to cover much of the surface. The close-up frame, bottom left, presents a surprising smoothness in this highest resolution view of Callisto's surface, 30 meters per picture element. Isn't it crazy to think that we have pictures of other objects in the solar system with such a high resolution? Last but not least, in 2000, the Cassini spacecraft en route to Saturn acquired high-quality infrared spectra of the Galilean satellites, including Callisto. It acquired high-quality infrared spectra of the Galilean satellites. Also, New Horizon probe on its way to Pluto obtained new images and spectra of Callisto. Real images of what NASA discovered on Jupiter's hellish moon, Io. The first ever spacecraft to pass by Io were the Pioneer 10 and 11 probes. It was a cold December 1973 here on Earth. With the help of radio tracking technology, Pioneer helped us to estimate the moon's mass, which, along with the best available information of its size, suggested the composition of mainly silicate rock rather than water ice. Then in 1977, NASA decided to send 2 probes to visit Pluto. Those were the Voyager probes. The journey would have been long because of the long distance to cover in order to reach it. When the twin probes, Voyager 1 and Voyager 2, passed by Io in 1979, their more advanced imaging system allowed for far more detailed images. It was March 1979. Voyager 1 flew past Io at a distance of about 20,000 kilometers. Very close. The precious images taken showed a multicolored landscape devoid of impact craters. It was such a strange surface. The highest resolution images showed Io as a relatively young object, with mountains taller than Mount Everest and features resembling volcanic lava flows. Navigation engineer Linda A. Morabito noticed a plume emanating from the surface in one of the images. Further analysis showed 9 such plumes scattered across the surface, and that was the final evidence for volcanic activity on the moon. This was actually a confirmation for a theory that has been proposed before the Voyager mission took place. Astrophysicist Stan Peele calculated that Io's interior must experience something called tidal heating. This process on Io is caused by an orbital resonance with Europa and Ganymede. Such heating is dependent on Io's distance from Jupiter, its orbital eccentricity, the composition of its interior, and its physical state. The tidal forces experienced by Io are about 20,000 times stronger than the tidal forces Earth experiences due to the Moon. The friction or tidal dissipation produced in Io's interior due to this varying tidal pull, which, without the resonant orbit, would have gone into circularizing Io's orbit instead, creates significant tidal heating within Io's interior, melting a significant amount of Io's mantle and core. The huge amount of energy produced is released in the form of volcanic activity, generating the observed heat flow. Other moons in the solar system are also tidally heated, and they too may generate additional heat through the friction of subsurface magma or water oceans. This ability to generate heat in a subsurface ocean increases the chance of life on bodies like Europa. When Voyager 2 passed by Io in July of 1979, it took some pictures as well. When scientists compared images taken by the two spacecraft, they noticed that several surface changes had occurred in the 4 mounts between the encounters. This makes Io one of the most hellish moons of our solar system. Finally, in 1995, the Galileo spacecraft arrived at Jupiter. The Galileo mission was entirely dedicated to the study of Jupiter and its moons. Ladies and gentlemen, prepare yourself because you are going to take a look at the most breathtaking pictures we have of Io. Here they are. Despite the lack of close-up imaging and mechanical problems that greatly restricted the amount of data returned, several significant discoveries were made during Galileo's primary mission. For example, we observed the major eruption at Pilin Patera volcano and confirmed that volcanic eruptions are composed of silicate magmas with magnesium-rich compositions. Another important revelation we had from Galileo was that Io doesn't own a magnetic field. But the game was not over. After some years, another interplanetary space probe was launched by NASA. It lifted off on January 2006. Its name was New Horizon, and it was the fastest man-made object ever launched from Earth. New Horizon again was meant for Pluto, but of course, if you happen to pass near to Jupiter, you won't miss your chance to take some beautiful pictures of it and its moons. It made its closest approach on February 28, 2007. The Jupiter flyby provided a gravity assist that increased New Horizon's speed. In doing this, we gained more data about the planet's atmosphere, moon, and magnetosphere. New Horizons also captured images of a volcano near Guru Patera in the early stages of an eruption, and several volcanic eruptions have occurred since Galileo. Here is a Jupiter and Io montage taken by New Horizon. Instead, here are shown changes on Io's surface. And we also have a plume fall. The last important spacecraft that gifted our eyes with beautiful pictures of Jupiter and its moons was the Juno spacecraft. It was primarily aimed at improving our understanding of Jupiter's interior, aurora, and polar atmosphere, and in order to do so, it has a highly inclined orbit that helped better characterize Jupiter's polar regions. Juno was launched in 2011 and reached its orbit around Jupiter in 2016. During several orbits, it has observed Io from a distance using JunoCam, a wide-angle visible light camera to look for volcanic plumes. Here's a visible domain image of Io from JunoCam, showing a volcanic plume illuminated beyond the terminator of Io. The image was taken on December 21, 2018, during the 17th flyby of Jupiter by Juno. While the new Juno images were taken a lot farther away from Io than the previous ones, there is still a lot of information that scientists can't obtain from them. For instance, they can provide new insights into how Jupiter interacts with its 5 moons, causing phenomena such as Io's volcanic activity or the freezing of the moon's atmosphere during an eclipse. Even though Io is very small, its gravitational interaction with Jupiter drives the moon's volcanoes, which produce high umbrella-like plumes of sulfur dioxide gas and extensive lava fields. That stretching causes friction and intense heat in Io's interior, sparking massive eruptions across its surface. Juno was the last mission that took pictures of Io.